today we shall consider pumping lemma for regular sets. This is very useful in proving certain sets are not regular. For example, you know that a power n, b power n is not regular. You cannot generate it with a right linear grammar, or you cannot accept it with a FSA. Why? The finite state automaton has a finite amount of memory, and if you want to accept a power n, b power n, it should some way remember n, but it cannot remember infinite number of values. So, it is not intuitively this is the argument, but formally we can use what is known as a pumping lemma and prove it. Now, what is the pumping lemma? The pumping lemma is like this. Let L be a regular set, then there is a constant n such that if z is a word in L and z, the length of z is greater than n, then you can write z in the form UVW such a way that the length of UV alone is less than or equal to n, and V is non-empty, its length is greater than or equal to 1, such that for all I greater than or equal to 0, U V power I W is in L. This is called the pumping lemma for regular sets. The idea is very simple. Look at the structure of a word Z accepted. Suppose Z is say A1, A2, AM, and M is greater than N, greater than or equal to N actually, that does not matter. You start with Q0, and after reading some portion you reach a state Qi, and then you reach a final state say Qm. Now, initially start with Q0, after reading A1 you go to some Q1, after reading A2 you go to Q2 and so on. After reading AM you go to the final state, and A1, A2, AM is accepted by the automaton. Now, if M is greater than N, how many states are there? There are M plus 1 states here. Okay. Suppose the DFSA has n states, suppose DFSA has n states, the n corresponds really to the number of states. Furthermore, n is no greater than the number of states of the smallest DFSA accepting L. So, L is accepted by a machine having n states, and Z is accepted by going from Q0 to a final state Qm. Now, you see that Q0, Q1, Q2 there are m plus 1 of them, and you are having only n states. So, by pigeonhole principle, some Qi and some Qj will be equal, they will be the same, right. You cannot have m plus 1 different states, so 2 of them will be equal. So, from say Qi is equal to Qj, then starting from Q0 and I is less than j, say I is less than j, then starting from Q0 after reading A1, A2, Ai you go to Qi, then after reading Ai plus 1 to Aj you go to the same state, Qj is the same as Qi, and from Aj plus 1 to Am you go from this to the final state, right. You have a string Z A1, A2, Am accepted by the machine, and the length of that is greater than n, the number of states of the deterministic automaton. Then there is a sequence of states which leads you to acceptance, and these states all cannot be different. From Q0 after reading A1 it goes to Q1, after reading A2 it goes to Q2 and so on. there are m plus 1 states in this sequence and totally you have only n different states. So, 2 of them have to be equal by pigeonhole principle, right. So, Qi is equal to Qj, say where I is less than j, then starting from Q naught, after reading A1, A2, Ai, you go to this state, and after reading Ai plus 1, Ai plus 2 to Aj, again you go to this state, and Aj from here after reading Aj plus 1 Am, you go to the final state, right. Now, you can see that A1, A2, Ai, Aj plus 1 Am will be accepted. Is not it? From here to here, then here to here, it will be accepted, right. And then A1 to Ai, then Ai plus 1 to Aj, starting from here you can go here and you can traverse this path any number of times you want, right, and then go to the final state. This will also be accepted by the same DFSA. It is a very simple concept. So, Z you can write, this you can call as U, this you can call as V, and this you can call as W. So, Z you can write as U, V, W such that U, V power I, W belongs to L for I greater than or equal to 0. When I is 0, it is UW like this. When I is 1, whatever you had earlier UVW, I is 2 is this UVWW and so on. So, the idea is here is very simple. Now, look at the statement of the lemma. When the length is greater than n, it may be written in this form such that uv less than or equal to n and v length of v greater than or equal to 1. That is, v is not empty. We are considering a deterministic automaton. Length of uv is less than or equal to n. Why? Because if you see a1, a2, an plus, you are taking a string like this, right. So, start from q naught, after reading a1 you go to q1, after reading a2 you go to q2, after reading an you go to qn. So, among the q naught, q1, q2 there are n plus 1 states. Here itself something has to repeat. You have only n states in the DFSA, and in this sequence you are having n plus 1 states. So, by the pigeonhole principle, here itself some qi and some qj will be equal. Okay. So, the uv portion will occur within this, right. So, the rest of the portion you can consider as, I mean, after the pump you can get the rest of the portion as w. So, uv portion will occur in this. So, that is why you say length of uv is less than or equal to n. Length of uv is less than or equal to n, and two of them are repeated even if it is a single symbol qi, qj, even if qj is qi plus 1, you would have read one symbol at least, is not it? Two of them are equal. Even if you take the worst case, that is successive states are identical, going from qi to qi plus 1, you would have read one symbol, right. So, the length of v is length of v, it is not empty, it is at least one symbol, it can be more than that. So, you have these two conditions, length of uv is less than or equal to n and length of v is greater than or equal to 1, right. So, that is all the proof. So, let us look into the statement again. Let L be a regular set, then there is a constant n such that that constant is really the number of states of the DFSA. If Z is a word in L and the length of Z is greater than n, that is if you have a sufficiently long string accepted by the machine, then you can pump the middle portion u v power I Z you can write as u v w such that u v power I belongs to L. Okay. Note that you can also have u empty. V cannot be empty, but u can be empty. The pump can occur in the beginning itself, it is possible. See, from here itself the pump can occur. Okay. So, because you are putting more and more V, it is called pumping lemma. You are pumping the middle portion, is not it? V squared, V cubed like that. That's why the name pumping lemma for this. Now, this is useful in showing that certain sets are not regular. This is useful in showing certain sets to be non-linear. Can show some sets are not regular using this lemma. Let us take the simple example a power n, b power n, n greater than or equal to 1. This is not regular. Intuitively the argument is you cannot, finite state automaton cannot remember everything. If it has to accept a power n, it has to remember every n. It is not possible with a finite amount of memory. Even in the case of carry, in the case of binary adder which we considered earlier, it just distinguishes between two classes of input histories. One is that which produced a carry and that with a one with carry and another without carry, right. It distinguishes only between them. You cannot know each and every possible input history. So, if it has to accept a power n, b power n, it has to remember after reading the entire A sequence of A's, it has to remember how many A's it has read. That is not possible by a finite state automaton. This is the intuitive argument. Let us use the pumping lemma. Here. Suppose the argument you have to write like this. Suppose L is regular, then L will be accepted by a FSA by pumping lemma. There is a n, there is a n such that if Z belongs to L and length of Z greater than n, Z can be written in the form UVW such that U v power I W belongs to L. This is the pumping lemma. Now, consider a power m, b power m, where m greater than n, where m is greater than n. So, you have a string a followed by an equal number of b's. Now, using pumping lemma, this can be written in the form UVW, and the other condition is length of UV is less than or equal to n and V is greater than or equal to 1. So, the pump UV portion will occur here. So, suppose something like this is there, this is V and this is W. V will not fall into B, UV will fall within the A portion. We have chosen that way. You have taken one string A power m, B power m where m is greater than n, right. So, the UV portion will occur within this. Suppose V is some A power P, okay. Then what happens? U is some A power Q, W is A power R, B power M, where what do you have? P plus Q plus R is equal to M, isn't it? So, you have A power Q, A power P, A power R, B power M. The string is of this form. P plus Q plus R is equal to M, and you can pump this portion. So, you will get A power Q, A power P, I, A power R, B power M belongs to L for all I greater than or equal to 0. That means, you can get A power Q, A power R, B power M belonging to L, you can get A power, so many strings you can get, where the number of A's will not be equal to the number of B's, right. If it is a regular set, it has to satisfy the pumping lemma, and if it satisfies the pumping lemma, you come to the conclusion that there are strings of the form A power n, B power m, something like that, where the number of A's is not equal to the number of B's, and such a string will belong to the language. You come to that conclusion, but that is not correct. The language L has strings of the form where you have only equal number of A's and equal number of B's, string of A's followed by an equal number of B's, okay. So, here you are arriving at a contradiction, therefore, L is not regular. Okay. Any questions? Let me work out one more example. The argument is similar. Instead of this, I will consider A power n square. You want to show that A power n squared is not regular. Suppose L is regular, then L will be accepted by FSA, and the pumping lemma there is a n such that if the length of n z is greater than n, then z you can write in this form such that u v power I belongs to L. Now, here consider A power n square. It is a string of A's, and the first UV, okay, let L be accepted by DFSA with n states. That is, the n is for the pumping lemma. So, if you take A power n squared, you can write it like this, and the UV portion will be within the first n symbols. Okay. So, suppose you consider length of UV is less than or equal to n, and length of V is greater than or equal to 1. So, length of V alone will be between 1 and n. And this is, some portion is u, some portion is v, and then it is w. So, if you consider u v square w, what can you say about the length? The length of this will be length of u v w plus length of v, but what will be the length of u v w? You have taken A power n squared. So, it will be n squared plus whatever it is, but it is less than or equal to n, is not it? Length of V is less than or equal to n. So, you get something a power some p or something whose value of p is n squared plus n. It is less than or equal to n squared plus n, it will be greater than n squared. So, after n squared, the next string you get is a power n plus 1 square, is not it? If you write the language, L will be a power 4, a power 9, right, then a power n squared, the next string will be a power n plus 1 squared and so on, is not it? And n plus 1 squared is n squared plus 2n plus 1. So, by this argument you are getting a string which is between, whose length is between this and this, which is not possible. In the language, the string whose length is high, next longer string than a power n squared is a power n plus 1 squared. But by this argument you are getting a string whose length is in between n squared and n plus 1 squared, which is not correct. Okay. So, you are arriving at a contradiction. Therefore, L is not regular. Many other languages you can show to be non-regular using this argument. Now, pumping lemma says that L is regular, pumping lemma holds, right. The argument, the way we have done is pumping lemma does not hold, so L is not regular. So, what we are proving? Proving the contrapositive. We are proving the contrapositive. This is of the form P implies Q. What we are showing is not Q implies not P, to show that this is the argument we are giving to show that something is not regular. And it is like an you can look at it as a sort of a game between two people. You are saying that you are choosing L, you want to show L is not regular. The adversary chooses N, okay. He can choose any N, okay, but once he chooses some N, he keeps straight. Then you choose Z, the way you choose Z you may choose depending on N, okay, that is what we have done. See, we chose a power m, b power m, where m is greater than n, or a power n squared, is not it? So, the adversary chooses n and you are choosing Z. Then the adversary can write Z in the form UVW for some UVW satisfying the condition UV is less than or equal to n and V greater than or equal to 1. Then you show that UV power KW does not belong to L for some K. You show that this is not possible, right. That is why it is not regular. This is the way it goes, okay. So, here if you look at the statement, for all L, well L is a regular set, there exists N for all Z such that Z of Z is Z belongs to L and then length of Z greater than N. There is a way to write it in the form Z is equal to UVW, okay. The statement of the pumping lemma, if you look at it, then for all I z u v power I v belongs to L. This is the way the pumping lemma, it is sort of you use the quantifiers in an alternate manner. For any regular set, for all regular or for any regular set, the regs n for all z belonging to L such that length of z greater than n, z can be written in the form UVW. There is a way to write z in the form such that UV power I W belongs to L, and you are corresponding to the for all quantifier. The adversary is the there exists quantifier. So, you first choose L, then the adversary chooses n, then you choose z depending on n. You can also fix the z once you know what is n. Then the adversary can write it in the form UVW. You show that for some k, UV per k does not belong to L. This is the sort of argument we give for proving some sets are not regular. Now, P implies Q, this is of the form, and what we have used is not Q implies not P, contrapositive. What is the converse? What is the converse to pumping lemma? It will be of the form Q inverse P, is not it? Converse is this. If you make a statement, it will be like this: if there is a n such that for any z belonging to L and L is some language, okay, so you start with L is some language, then if there is a n such that for any z of length greater than n, you can write z in the form UVW such that UV power I W belongs to L for all I, then L is a regular set, isn't it? The converse will be of that form. Is it true? Is the converse true? Do you think it will be true? How many of you think it is true? Converse will be true. How many of you think it is not true? Huh? How many of you think the converse will be true? I can't say. Converse is not true. Converse is not true. For that you consider, that is, the pumping lemma may hold, L may not be regular. If the pumping lemma does not hold, L is not regular. But if the pumping lemma holds, you cannot conclude L is regular. L may be regular or non-regular, you cannot say. So, take L to be A power n, B power m squared, n greater than or equal to 1, n greater than or equal to 1. Consider this. Is this a regular set? This is not a regular set, okay. Number, you can have a sequence of A's, but the sequence of B's is m squared. So, this is not a regular set, but if I choose n instead of n, see, I do not want to use the same n, maybe I will say a power p, p greater than or equal to 1 and m greater than or equal to 1. Suppose this satisfies the condition for all there is a n, then you can choose a string. See, the p is greater than or equal to 1, there will be at least one a. So, the string will be of the form a, b. If you take a string of length n, whatever it is, the first symbol has to be a, it cannot begin with a b, right, and the pump you can just pump a, the first symbol alone you can pump, then the resultant string will be in the language, isn't it. this union. You have to also have b power q, q greater than or equal to 1. Some sequence of A's, non-empty string of A's followed by a sequence of B's. Sequence of B's will be of the form m squared, otherwise just sequence of B's alone. The reason for that, if you take I to be 0 and you start with the string say A, B, B, B something, if you pump A, I is equal to 0, you will just get a string of B's. This you can pump I times I, if you take to be 0, you have to get a string of B's, okay, sequence of, that is why this is anyway this is not regular, you can see that this is not regular. Because of this portion, you have a sequence of A's followed by the sequence of B's, which is not of a form, it is of this form, so it is not regular. But you can have any sequence of B's, without A's you can have any sequence of B's. This portion is regular, does not matter, but the whole thing is not regular. So, the converse to pumping lemma is not true. There is something like a converse to a pumping lemma, which is a very involved theorem. It is not given in any book, I think it is only in the paper. There is a result by Ehrenfeld, Rosenberg and Parikh. Ehrenfeld, Parikh and Rosenberg, which is something like a converse to pumping lemma, which assumes more conditions. And then you show that under these conditions, it is not only pumping lemma, you identify certain positions and say that certain things can occur and so on, then L will be a regular set, something like that. With this condition alone, the converse is not true. Moreover, you must realize that what pumping lemma says is, if you have a string whose length is sufficiently large, then Z can be written in the form UV power UVW such that UV power I W belongs to L. You can keep on incrementing I can be 1, 2, 3, it can go up to infinity. So, you will get an infinite number of strings beginning infinite number of string which belong to L. It does not mean that if you have a sufficiently large string, you have a sufficiently large string belonging to L, you can write it in the form UV power I W for large I. That is not true. What pumping lemma says is, if you have a fairly large string, then you can write it in this form and you can get infinite number of strings of this form. It does not mean that if you have a very large string, you can write it in this form UV power I for large I. One example is, simple example is sigma star, where sigma is AB. You know that there are large strings which are cube free. We have seen that there are large strings which are cube free. That is, no substring will occur 3 times consecutively. Okay? So, this is what it means. We can make use of this to show that other things like WCWR is not regular, A power PP is a prime not regular, A power 2 power n n greater than or equal to 0, not regular, and so on. Actually, it is important to show that certain sets are not regular, and there are three ways of doing that. One is use pumping lemma to show something in that, to show L is not regular. You can use three methods. One is use pumping lemma. The next method is use Myhill-Neroth theorem. This we shall be considering next. Third, the Parikh mapping. Is not semi-linear. This is another way you can show. These two things we shall consider later. Now we shall consider the pumping lemma for context free languages. For regular sets, what we found is, if the string is sufficiently long, then a portion of it can be pumped any number of times. For context free languages, what we will find is, given a context free language, if you have a string which is sufficiently long, then two portions of the string can be pumped equal number of times, so that we get an infinite number of strings. So, the statement can be like this: let L be any context free language, then there is a constant n depending only on L, such that if z is in L and the length of z is greater than or equal to n, then we may write z as UVWXY, such that length of Vx is greater than or equal to 1. What it means is, both V and x cannot be simultaneously epsilon. And second condition is, length of VWX is less than or equal to n, and for all I greater than or equal to 0, U V power I W x power I y is in L. That is, both the portions V and x can be simultaneously pumped equal number of times. Now, you can see that if you have a sufficiently long string in a language, the corresponding parse tree should have a path which is sufficiently long. In fact, we can show this. We can show by induction on I that if the parse tree of a word generated by a Chomsky normal form grammar has no path of length greater than I, then the word is of length no greater than 2i minus 1. So, in order to prove the pumping lemma, first we shall take the context free grammar to be in Chomsky normal form. Let the context free language minus epsilon, we are not very much bothered about epsilon, because we are going to consider only strings of length greater than or equal to n for a large n. So, let L minus epsilon be generated by a context free grammar in Chomsky normal form. Let the number of non-terminals in the CFG be k, then we take n to be 2 power k. Now, in this grammar we can show that if the parse tree of a word generated by the Chomsky normal form grammar has no path of length greater than I, then the word is of length no greater than 2 power I minus 1. For the basis I1 is trivial since the tree must be of the form shown in the figure. If the path length is 1, you have a situation like this. The length of the string generated is 1. You see that I is 1, so 2 power 1 minus 1 is 2 power 0, which is 1. Okay. So, the basis clause holds. Now, for induction, assume that the result is true up to path length I minus 1 and show that the result is true for path length I. Now, you consider this tree with path length maximum I, then the first step of the tree will be like this, and from this non-terminal there will be a subtree here, there will be a subtree here. The maximum path length in T1 or T2 will be I minus 1. So, the maximum length of the string generated in this portion will be 2 power I minus 2. Similarly, the maximum length of the string generated here is 2 power I minus 2. So, the total length of the string generated by this tree will be 2 power I minus 2 plus 2 power I minus 2, which is 2 power I minus 1. So, this proves the simple result. Now, let G have k variables or k non-terminals and we take n to be 2 power k. If Z is in LG and the length of Z is greater than or equal to n, then because the length of the string is greater than or equal to 2 power k minus 1, any parse tree for Z must have a path of length at least k plus 1. If it is less than that, then the string will not be of this length, but such a path will have at least k plus 2 vertices, and the last one will be a leaf, rest of them will be non-terminals, and there must be some variable that will appear in the path. So, let us consider like this. The tree has a path of length k plus 1 or more, right. Now, let this be the longest path. There may be 1 or 2 such paths. Let us take one of them. You find that the last one will be a terminal symbol, rest of the nodes in this path will be non-terminals, and there are only k non-terminals and there are k plus 1 nodes with labels which are non-terminals. By the pigeonhole principle, at least one non-terminal will be repeated, that is somewhere here, the same non-terminal will be repeated as the label of the internal node. In fact, we can say something more than that. Some variable must appear twice near the bottom of the path. This you can say. In fact, let P be a path that is as long or longer than any path in the tree, then there must be 2 vertices V1 and V2 on the path satisfying the following conditions. The vertices V1 and V2 both have the same label A. The vertex V1 is closer to the root than vertex V2. The portion of the path from V1 to the leaf is of length at most k plus 1. How can you get this? So, in the derivation tree for Z, take the longest path. If there are more than one, take one of them. Start from the leaf, go up the path up to a path length of k plus 1. You consider a path length of k plus 1 here. In that, there will be k plus 1 non-terminal nodes, that is nodes with labels as non-terminals. The last one will be a leaf. Among this k plus 1, by the pigeonhole principle, 2 of them will have the same label A, say. Call this as V1, call this as V2. So, V1 is nearer to the root than V2 and both of them have the same label. The path from V1 to the leaf is at most k plus 1. In the worst case this can be A, otherwise somewhere A will be here. So, the path length from V1 to the leaf will be at most k plus 1. Now, if you consider this result of this tree, the string derived, let it be Z1, this one is Z1, and from this another tree will be subtree will be derived, call this as Z2. So, you can write Z1 as Z3, Z1, Z4. This portion is Z3, this portion is Z4. You can see that both Z3 and Z4 cannot be epsilon simultaneously. One can be epsilon possible, but both of them cannot be epsilon. The reason is, from here you use a Chomsky normal form grammar, so it can be like this, and this subtree will entirely lie within one of them. Either in this case it lies on the left of it, left subtree, sometimes it may lie on the right subtree, but whatever it is, the other tree will be non-null, and so you have this feature. Thus, we find that a tree T1 with V1 represents the derivation of a subword of length at most 2 power k, and this is true because there can be no path in T1 of length greater than k plus 1. So, in the figure what we saw is the length of the string derived from the first A, that is V1, is at most 2 power k. That is why we have the first condition in the theorem, or maybe the second condition in the theorem, length of UVWX is less than or equal to n. And P has a path of longest length in the entire tree. Let Z1 be the yield of the subtree T1, T2 is the subtree generated with the vertex V2, and the string generated by that is Z2. So, you can write Z1 as Z3, Z2, Z4. Both Z3 and Z4 cannot be epsilon, since the first production used in the derivation must be of the form A goes to BC for some variables B and C, and the subtree T2 must be completely within either the subtree generated by B or the subtree generated by C. So, we have this result. As an example, you can consider this. You consider this example where the grammar is given by 3 non-terminals, it is in Chomsky normal form. Rules are A goes to BC, B goes to BA, C goes to BA, and so on, A goes to A, B goes to B. You see that you have a generation for this tree. Now, if you consider a path, what is k here? K is 3. So, consider a path of length 4, start from this 1, 2, 3, 4. In this you find that the non-terminal A is repeated here. So, V1 is nearer to the root than V2, and V1 and V2 have the same labels. The result of the subtree with this as the root, you look at this, then this generates Z1, BBA is Z1. What is Z2 generated by this subtree, that is just this A. So, Z1 is BBA, Z2 is A, Z3 is BB, this portion, and Z4 is epsilon, because this entirely falls on one side. So, what you have is Z1 can be written in the form Z3, Z2, Z4, where Z3 is BB and Z4 is epsilon. So, what you find is from the non-terminal A, you are deriving Z3 A Z4 . Now, this portion you can repeat any number of times. Actually, if you repeat this any number of times, Z3A, Z4, Z3A, Z3, Z4, Z4 and so on. You can pump Z3 any I times and the same number of times Z4 also will be pumped. Now, if in the theorem we take Z3 to be V, Z2 to be W, Z4 to be X, starting from S you will have a derivation UAY. Okay. If you look into this tree, right, some portion will be generated here, that is U, and some portion will be generated here, that is Y. We are bothered about this portion, and here this can be, these two portions can be pumped. So, from this A you can generate Z3 and Z4 any number of times simultaneously, that is V can be generated any number of times, X can be generated any number of times, and then finally from A you will derive Z2. A also derives Z2. So, and Z2 is nothing but W. So, U V power I W X power I Y. Okay. So, we get the pumping lemma for context free languages. Let us see how the pump occurs. You see that in this example which we considered earlier, see, look at this example, this is Z1, right. So, on the left you are getting a portion of the string which is B, on the right you are getting a string BA, right. So, U is B and Y is BA, right. So, U is B and Y is BA, and in between this BB is the portion V. This can be pumped any number of times, BB, 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 like that it can be pumped any number of times. X is epsilon, even if you pump it several times you are going to get epsilon only, and finally the derivation ends with a A, W is A, you get here. So, this BB can be pumped any, this portion is pumped any number of times, that is what is shown here. So, once, twice, like that it can be shown, it can be pumped any number of times. So, this is called pumping lemma for context free languages. How can this be used? The pumping lemma can be used to show that certain languages are not context free. For example, we can show that A power n, B power n, C power n, n greater than or equal to 1 is not a CFL. It is a context sensitive language. How can we show that this is not a CFL? Okay. Actually, what we are going to prove is, if L is a CFL, then pumping lemma holds. The contrapositive of it will be, if the pumping lemma does not hold, L is not a CFL. Okay. So, in order to show that, assume that pumping lemma holds for L, this L, then show you arrive at a contradiction. Let n be the constant of the pumping lemma. Then consider the string a power n, b power n, c power n. So, you have a string of a's equal number of b's equal number of c's. Now, this can be written as UVWXY, where the length of VWX is less than or equal to n. So, this VWX portion can occur within A or within A, B or within C, or like this. It cannot occur like this. It cannot include both A and C. It can include A and B, or it can include B and C. It can include just one symbol, that is also possible, but it cannot include A and C. So, when you pump U V power I W x power I, Y will belong to L, and you will find that when you pump, if the portion is like this, V W x portion is like this, the number of A's will increase, number of B's will increase, but the number of C's will remain the same. If the portion is like this, number of B's and C's will increase, but the number of A's will remain the same. So, you will get a string which has unequal number of A's, B's and C's. You will get a string with unequal number of A's and B's and C's, which is a contradiction. Therefore, L is not a CFL. Thus, we can use the pumping lemma for context free languages to show that certain languages are not context free. We can use it for languages like a power n squared, n greater than or equal to 1, or a power 2 power n, n greater than or equal to 0, and so on. Thus, we have seen the pumping lemma for regular sets and also the pumping lemma for context free languages. One thing we have to note is we use the automaton, the finite state automaton for regular sets, and we use the context free grammars for proving the pumping lemma for context free languages. Both are similar in the sense that you can pump a portion. If it is a regular set, you can pump two portions simultaneously for a context free language.